All right, Unit 3 starts out, as you'll notice probably right away just by the size of the notes, that this unit is much shorter than Unit 2, which is good in some ways, in that there's less you have to remember, but it doesn't really matter. You have to know all of it, no matter what. So, the beginning of Unit 3 begins with balancing equations. Okay, so I just want to highlight a couple things about balancing equations, and I'm going to do some examples with that. Okay, when you balance an equation, the only thing that you can change are what are called the coefficients. Okay, the coefficients are the numbers that go in front of the chemical formulas. So when you're writing a chemical equation, you have to make sure the formulas are correct. If they're not correct, you might find that the equation will never ever balance. Okay, so you want to make sure that when you're writing out a chemical formula before you start the balancing process, that equation is written correctly. Again, if you keep going back and forth where it won't ever balance, it's probably because you've written at least one or more of the formulas incorrectly. So when we do this, we're not worried about, again, when we're balancing the equation, you do not have to include the solids, liquids, gases, and aqueous. Those are there mainly just to help you know what state things are in. So on the AP exam, if you're asked to write a balanced equation for a reaction, and we haven't talked about this yet, don't worry what that is yet. Okay, it is not necessary to write the state symbols, the solid, liquids, and gases. Okay, but whenever they write them, they will always have the solid, liquid, gas, aqueous there. Okay, so I'm going to do these first examples here with you. Again, all we're trying to do is when we balance an equation, we're obeying what's called the law of conservation of mass. Not something you have to remember. Okay, the law of conservation of mass, sometimes it's also called the law of conservation of matter, says that every single atom has to be accounted for. You can't lose any atoms in a chemical reaction. I didn't say nuclear reaction. That's not part of the AP curriculum. But in a chemical reaction, every single atom has to be accounted for, which means the number of the atoms on the reactant side have to equal the number of atoms on the product side. Every single atom has to still be there. It's just going to be rearranged a little bit differently, and you have to balance those out. So when you do that, typically I just start with the very first element. So I can see that on the reactant side, there's one calcium atom, and hey, there's one calcium atom on the product side. So every calcium atom has been accounted for. There's nothing that we have to do to fix that. Okay, and then I go to hydrogen, and I see that there's two hydrogen atoms here. On the product side, there's these two hydrogen atoms, and this is an easy mistake to make, but that 2 goes, like the, what's that called, the distributive property. The 2 goes to everything inside the parentheses. So that means on the reactant side, there's 2 hydrogen atoms, but on the product side, there's 4. Okay, you can't magically come up with 2 extra hydrogen atoms. Those had to have come from somewhere. So instead of just 1 water molecule reacting, it had to be 2 water molecules. And notice, again, the coefficients are the numbers that go in the front. Remember, when you balance an equation, those are the only numbers you can change. You can't change the chemical formulas at all. And when you put a 2 in the front, the 2 goes just like over here, like the distributive property, the 2 goes to everything. So that's 2 oxygen atoms in H2O, and then again over here we've got our 2 oxygens in the calcium hydroxide. Okay, and so if I can erase most everything, that is the balanced equation. There, 1 calcium atom will react with 2 water molecules to make a hydrogen molecule and a particle of calcium hydroxide. Okay, let's look at letter B. Again, 1 copper, 1 copper. Okay, and that's great. I mean, if it's maybe it's already balanced before you even do anything. That would be awesome. It's not fully, but the copper is. Okay, because then we can see there's 2 oxygen atoms on the reactant side, but there's only 1 on the product side. So again, the only thing we can change are those coefficients. So that's 2 CuOs, and therefore by fixing the oxygens, we broke the coppers, so we need to put a 2 right there to balance the coppers, and that equation is now balanced. Okay, on letter C, we've got 1 sodium. On the product side, we have 2. So I'm going to put a 2 right there. And then you just go element by element. And then there's 2 oxygens. Oh, over here there's only 1. Well, then I need to put a 2 there. And then again, just like in the previous one, sometimes when you fix one thing, it breaks something else. Okay, because now there's 2 oxygens, but now there's 4 sodiums all total. So we need a 4 right there. Okay, letter D. 1 iron, 1 iron. 1 hydrogen on the reactant side, 2 on the product side. So I need a 2 right there. And then there are 2 chlorines on the reactant side, 2 chlorines on the product side. That's it. Okay, letter E. 1 iron, 1 iron. 2 bromines, 3 bromines. So we got to get to the same number. So we're going to put a 2 there and a 3 there. And then by doing so, we also have to go back and fix the iron. So we do need to put a 2 there. Now, you will see sometimes, they'll never tell you to do this, but you may see them sometimes. For example, on this, not a plus there, sorry. On this very one right here, you could see something like this, where if they write the balanced equation, they might do this. They might put a 3/2 right there. Because if you have 1.5 bromines, well, then that's 3 bromines all total on the product side. Okay, so 3/2 Br2 equals 3 bromines. Now, again, they'll never ask you to balance an equation. I just want you to know that if you see a fraction, don't freak out. Oh, that's wrong. Technically, yes, you can't have 1.5 bromine molecules. But in terms of, for simplicity, a lot of times they will use fractions. Don't worry about that. As you know, if they do it, it's not a big deal. Okay, letter F, C4H8 plus O2. So we got 4 carbons. So we need 4 carbons. And then we have 8 hydrogens. So we need 8 hydrogens. And then, now let's count all total. We have 4 times 2 is 8. I'm looking at the product side here. 4 times in CO2, there's 8 oxygens. And then in water, there's 4 more. So 8 plus 4, 12 oxygens all total. So we do need a 6 right there. A lot of times what they try to do to mess with you is they do a problem like this. Okay, and the reason, let me just show you this one here real quick. The reason that it messes with you, because you go, oh, well, 1 carbon, that's a C, sorry. And then 3, don't forget about this hydrogen here. That's 4 hydrogens all total right here. So I need a 2 right there. And then you go, oh, 2 oxygens plus 2 more oxygens is 4 oxygens. And you put a 2 right here to make 4 oxygens, because it's really, really easy to forget about that oxygen right there. Okay, so if we back that up, let me kind of start over here with this one. So CH3OH plus O2 makes CO2 and H2O. Okay, again, 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens. 1 oxygen plus 2 more is 3, but on the product side we have 4. Okay, when you have a problem like this where you have an odd even, you've got an odd number on one side and an even number on the other, the easiest way to solve that is make that odd number an even number by doubling everything. So I'm going to change that 1 methanol, CH3OH, to 2, which means now I need 2 CO2s, and now I need 4 H2Os. And what that does is, how many oxygens do I have all total on this side? 2 times 2 is 4 plus another 4. I have 8 oxygens over here. Over here I have 2 from there. And now I need 6 more, so I need 3 O2s. Okay, that's about as tricky as it gets right there if they ask you to balance. And you'll see, I'll show you some examples here in a minute of real questions. Okay, letter G. 2 sodiums, 1 sodium. Put a 2 right there. 1 carbon, 1 carbon, 3 oxygens. 2 plus 1 is 3. And then we have H, 1H. Here we have, on the product side, we have 2. So we need a 2 right there. And then 2 I's and 2 I's. We're good. Okay, letter H. Looks like you got 1 copper, 1 copper, 1 carbon, 1 carbon. 3 oxygens, 1, 2, 3 oxygens. Remember I said sometimes maybe everything's balanced before you even start? Then that's the case here. Okay, letter I. PbNO3 makes PbO plus NO2 plus O2. This is tricky because there's oxygen in every single thing. So let's worry about it at the end. So 1 lead, 2 nitrogens on the reactant side. So we need a 2 right there. And then that makes, here we have 6 oxygens all total. There's 2 O3s. So that makes 6 oxygens. On the product side, we have 1 plus 4 is 5, plus another 2 is 7. So we have 6 on one side, 7 on the other. Okay, that doesn't work. So we need more on this side. So the only thing I can do is instead of 1 PbNO3 I'm going to go to 2. Okay, let's see if that helps us at all. So 2 leads means 2 PbOs. And that makes, now be careful here because there's 2 nitrogen plus the 2 more nitrogens. So you've got to double nitrogen twice. That's 4 nitrogens. Okay, so we need 4 NO2s. And now on our reactant side, how many oxygens do we have all total? Be real careful here. We have 2 NO3s. So that's 6 oxygens. But then we have 2 PbNO3 So that's 12 oxygens on the reactant side. On the product side, we have 2. 4 times 2 is 8. That makes 10, plus another 2 is 12. So we actually do have the correct number of oxygens on both sides now, so we're done. Again, that's a pretty tough one right there, letter I. Okay, and if you can do those, great. I mean, you should be able to do them. It's just a little bit of back and forth getting to the right answer. Okay, letter J. You've got 2 hydrogens plus 1 more is 3, and here you only have 2. So I'm going to start by putting a 2 there because I know I'm going to need more. And then one of the tricks you can do is if like SO4 is here and SO4 is here, don't think of it as 1 sulfur and 4 oxygens. Think of it as I have 1 SO4 on one side, I have 1 SO4 on the other side. That'll make things a little bit easier for you. Okay, and then we have 1 potassium. Here we have 2. So we put a 2 right there. And then again, forget about the SO4s. We already took care of those. So we have 2 oxygens, and then we do have our 2 oxygens here as well. So that's good. And then hydrogens, we have 4 of both of them now. So that is balanced with 1, 2, 1, 2. Okay, letter K, 1 sodium, 2 sodiums. Put a 2 right there. 2 hydrogens, 2 hydrogens. 2 carbons, 1, 2 carbons, 6 oxygens, 3, 4, 5, 6, done. Okay, and then our last one, 1 aluminum, 2 aluminums, put a 2 there. 2 oxygens, 3 oxygens, so we got to get to 6, so we're going to put a 2 there. That means we need 3 O2s and 4 ALs. Okay, example 2. I'm going to move a little quicker through these. The reaction between hydrogen gas and oxygen gas can result in the formation of water. Describe any observations you might reasonably expect to make during this observation. This is a combustion reaction where the hydrogen is going to burn. So you might say, you might see fire, you might see an explosion. You're definitely going to see some type of, again, some energy release. Okay, a balanced equation for this is H2 plus O2 makes H2O. We do need to balance that. So we do have 2 oxygens here. Here we only have 1, so we need a 2 there and a 2 there. Okay, and then part C says give 2 reasons. So basically, a lot of times what they'll do is they'll take these balanced equations and then they'll put them as molecules and what's called a particle diagram. That's what this thing is. This is called a particle diagram, and they'll put that in there and ask you questions about it. So C says give 2 reasons why the diagram below represents a reasonable summary of the reaction. Well, you've got 2 hydrogens, and then you've got 1 oxygen molecule, and then you have 2 water molecules. So one of the reasons might be that it's balanced, that the number of atoms is correct, and another reason might be that the molecules are drawn correctly as H2s instead of H, O2, and then H2O like that. Okay. Just a couple more. So these are from a pretty recent exam, so this is kind of what you might expect. A scientist heats a sample of pure nonmetal Q in a closed container containing pure nitrogen gas. The reaction proceeds to completion. The unbalanced equation. Give the correct value of each stoichiometric coefficient for the balanced equation. So basically, 1 Q, 2 Qs. Put a 2 right there. 2 nitrogens, 2 nitrogens. Done. So that means that A equals 2, B equals 1, and C equals 1. That's all you got to do. Okay, this one was a little bit more challenging. Okay, you got to balance it, and again, they want the coefficients. So 1 selenium, 1 selenium. 1, 2 oxygens, 1, 2, 3, 4 oxygens. Okay, this one's a little bit tougher because I don't know. There's oxygen all over the place. Which one do I fix? Whenever that happens, this is a good example of wait for oxygen until the end. Typically, when you fix everything else, usually the oxygen will fix itself. Okay, so let's not worry about oxygen for right now. But here I do see 2 fluorines. Here I only see 1 fluorine, so I need to put a 2 right there. Okay, and then in terms of sodium, I see 1 sodium here. On the right-hand side, I see 4 sodiums. So I need a 4 right there. Oxygen, again, I'm not worried about oxygen. 4 hydrogens. Here I only see 2 hydrogens, so I'm going to put a 2 right there. Now, the problem is if we fix an oxygen, it's going to mess up something else. Everything else works right now. The seleniums are good, the fluorines are good, the sodiums are good, and the hydrogens are good. So now let's just check our oxygens. So we've got still the 1 oxygen here, but now we have 4 more. So we have 5 on the reactant side, and then we have 3, and then we've got the 2, we've got 5. So A equals 1, B equals 4, C equals 1, D equals 2, E equals 2, done.